Automatic Addison.
In this tutorial, we will create a simulated mobile robot from scratch. Our robot model will be in the standard unified robot description format. By the end of this tutorial, you will be able to build the robot that you see in the center of your screen. The robot we will build in this tutorial will have mecanum wheels, also known as omnidirectional robot. A mecanum wheeled robot uses special wheels with rollers attached at an angle, allowing it to move any direction by rotating the wheels independently. Compared to robots with standard wheels that can only move forward, backward, and turn, mecanum wheeled robots have greater maneuverability and can move sideways without changing orientation. Within ROS 2, defining the URDF file of your mobile robot is important because it allows software tools to understand the robot structure, enabling tasks like simulation, motion planning, and sensor data interpretation. It is like giving the robot a digital body that software can interact with. I will walk through all the steps for creating the URDF for the ROS Master X3 by Yaboom, a company that makes educational robots. Follow along with me, click by click, keystroke by keystroke. The first step is to create a ROS 2 package to store all of your files. So we've got a new terminal window open, and let's create a new folder called Yaboom ROS Master. CD. Let's go into the workspace, source folder. It's clear. Let's make the directory Yaboom ROS Master. Let's CD into it. Okay, and now let's create the package where we will store our URDF file. ROS2 PKG, create, build type, mint, CMake, license, BSD, 3, clause, Yaboom, ROS Master, description. Okay, ROS 2 package create, build type, meant CMake, license is BSD 3 clause, and the name of the package is Yaboom ROS Master description. There we go. Now let's create the meta package. Remember, a meta package doesn't contain anything except a list of dependencies to other packages. You can use a meta package to make it easier to install multiple related packages at once. So let's clear. All right, so let's do ROS 2 package create, build type, mint, CMake, license, BSD 3 clause, Yaboom ROS Master. Enter. So our meta package. Now let's go into it. And let's edit our package XML. Get it, package XML. All right. And here is what you should see now when you open your package XML for your meta package. And let's just go through it a little bit. So we've got the XML model, that's good. Package format 3, the name, the version. And in the description, let's clean that up a little bit. Let's just call it, let's say, ROS Master Series Robots by Yaboom. And then we're going to say meta package. Okay, automatic Addison at todo.com, BSD 3 license. Okay, everything so far, so good. Let's just add one dependency right now. So under build tool depend, we've got one package other than the meta package, and that's called Yaboom ROS Master description. Okay, we need to do exec depend. go slow Addison, exec depend, yaboom, ROS master description. And let's do exec depend. Alrighty. All good. Let's save. Let's close it. Now let's add a README to the main package. We're going to do cd ... And let's do get it README, read.me. Okay, and in your README, I want you to put the symbol for, let's see, what should we do now? So we're in the main yaboom ROS master, and let's just add the Ubuntu version and the ROS version so that people who come along and take a look at our code down the road will know what this particular package is compatible with in terms of the Ubuntu version as well as a ROS version. So I'm going to type this code, copy and paste it. Okay, and so we've got yaboom ROS master up top, which is the name of the whole package, the whole enchilada we have here. And we've got operating system. We're using Ubuntu Noble, Ubuntu 24. So make sure you get that HTTPS, that URL there. And then the ROS2 version, you can see we're using Jazzy. So make sure you use that URL there. Just take a moment and put that in there for the README. And this is mainly just a, kind of a placeholder for now. We'll fill it out later. All right, and let's go over to our here, which is our meta package. You're going to cd into the meta package. And I think it's good practice at this stage just to add a meta, so our README for the meta package. And let's open that now. Let's do get it readme.md. Okay, and let's see what we're going to do here. Let's just put the title, just a placeholder here. Pound yaboom _ ROS master. And then pound. Save. Close. Okay, so now we got that. That's a placeholder. And what about our yaboom robot ROS master description package? Let's do cd yaboom ROS master description. Get it readme readme.md. Okay, and let's do the same thing there. Yaboom ROS master description. Pound. Save. Okay. So now we've got everything. And remember our yaboom robot ROS master description package that we're in right now. This will contain the robot description files that describe the physical aspects of the robot, geometry, kinematics, dynamics, and the visual aspects. So before we start filling all that stuff in, let's just clear everything out. All right, let's cd back to the workspace, the root of the workspace. So make sure you're in the root of the workspace here, ROS2 _ WS, and type :build. Our favorite command, :build. All built nice and cleanly. Okay, and let's source the bash. Okay, and let's see if our packages are recognized. So ROS2 pkg list. Yaboom ROS master and yaboom ROS master description in all their glory. Now let's create some more folders. We're going to create some more folders that will house all of our artifacts for the URDF. Go slowly. So the first command that we're going to type is make dir is this one. So make dir. Okay, just go through it. Space -p, and then ROS2 workspace, source, Yaboom ROS master, Yaboom ROS master description, and then meshes, ROS master X3, and visual. Type all of that now and press enter. Okay, the next one is going to be a control folder that's going to be inside the URDF folder. So let's do that now. Some reason it's just giving me read only. Okay, so make dir, and they're going to do -p, tilde, ROS2 workspace, source, Yaboom ROS master, Yaboom ROS master description, URDF, and then control. Name of the new folder is going to be control. Okay, let's now press the up button on your terminal, and let's create another one that's mech. This will house the actual physical, modeled physical aspects of your robot. Physical structure, that's mech. Now let's do sensors. This will hold our sensors, like our LIDAR and depth camera. URDF files, enter. And now robots. Robots folder is where we're going to house the URDF that brings everything together. The control plugins, the mechanical structure of the robot, the sensors, all coming together in our robots folder. And press enter. Okay, now let's add the mesh files. Remember, mesh files are what make your robot look realistic in robotic simulation and visualization programs. So the mesh files we are going to use were already available in the Yaboom ROS master GitHub. I'll show you where that is. Yaboom ROS master X3 GitHub. It's this result here. So we're just pulling the files that were already available here from the public repository for the ROS master X3. And if you want to create your own custom 3D printed mobile robot in the future, all you have to do is use a program like CAD, CAD program on Shape, Fusion 360. You can use AutoCAD or SolidWorks. Just get a CAD program, and these tools will help you create the 3D models of your robot parts that you can then export into STL or Collada format for use as in your URDF for the mesh file. But we've already got all we need thanks to Yaboom, and so we're going to pull these mesh files off of my own GitHub. So let's go to CD, downloads, clear, and let's do a git clone, https://github.com/automatic/Yaboom_ROS_master.git. Let's clone that puppy. Let it download. It's a lot of files. Okay, everything's done. Now let's move the mesh files for the robot we are going to model. So copy, recursively, Yaboom, ROS master, Yaboom, ROS master description, meshes, then the asterisks, get everything in there. And let's do tilde, ROS2 workspace, source, Yaboom, ROS master, Yaboom, ROS master description, then meshes, enter. Okay, now let's just see if everything is in there. So let's do an ls, ROS, source, Yaboom, ROS master description, meshes, ROS master visual. There we go. All of our STL files are in there. Let's clear everything out. And now let's open Visual Studio Code so we can configure our CMakeLists.txt. So I'm going to go cd ROS2 source. Yeah, boom. Clear. Opening up Visual Studio Code. It might ask me for a password. Let's see. Okay, it did not. Okay, and let's go to the Yaboom ROS master description package, CMakeLists.txt, and let's take a look at it. Make sure everything's okay. Just go through. I'll add a dependency here on the URDF tutorial package. URDF tutorial required. Save. Okay. And okay, let's see. Okay, we need to add a piece here for some folders which we are going to create. So under the find package, I'm going to type a comment here, copy necessary files to designated locations in the project. All right, and we're going to do install. And let's do directory, config, launch, meshes, URDF, RViz. Okay, and destination, share, $, project name. Save. Build testing. All that is looking very, very good. Okay. And let's just make sure we have those packages inside the Yaboom ROS master description package. So cd Yaboom ROS master description. And let's just make sure we've got all the packages. So config, let's make that. Make dir config. Okay, what else we need? Launch. Let's do make dir launch. Meshes. Already got it. And RViz. So make dir and then RViz. So now we've got all of our folders that we need. And let's close. All right, now let's configure the package.xml for the Yaboom ROS master description package. So we got our name. Let's add a description right here. Contains the robot description. Files that define the physical aspects of a robot, including its geometry, kinematics, dynamics, and visual aspects. Okay, everything's good there. And down here, so we got build tool depend. Let's add a depend here. And let's do URDF tutorial. How we looking? How we looking? Close it out. Okay, and now let's go over here to, where shall we go? view terminal. Let's go to CD, ROS2, clear. Okay, and let's do ROS dep install I -- from path src, and then ROS distro Y. Okay, all required ROS deps have been installed successfully. Okay, now we need to build. And I've got an alias for that. I'll show you what it is. Alias. Okay, and build. You can see build. What I do is I CD into my workspace. I then type :build, and then I source the bash RC. So I've got an alias that already does that for me. So rather than typing CD ROS2 workspace :build and then sourcing the bash, I'm just going to type build, and it'll do it. All that automatically, and everything built just fine. Okay, now let's create some additional files. Follow with me. I'm going to get on the big terminal so you can see everything. All right, so let's go. Remember, go slow, go slowly, go slowly. Slow is smooth, smooth is fast. There is no rush. Enjoy the journey. So this is the first command. This is the first command. We're going to create multiple XACRO files. So touch ROS2 workspace source, yaboom ROS master, yaboom ROS master description, URDF, mech, and we're going to create a base URDF file. And this is actually for the robot base, the actual base chassis of the robot. And then we're creating a URDF for the wheel, mecanum wheel. So take a second, type that command into your terminal. All right. Now let's add on some more. So just do a space. And here we're going to add a RGBD camera, an IMU, inertial measurement unit, and a LIDAR. So type that in. And then finally, go space, and then here we're going to add a URDF for our full robot that brings everything together, the robot body and the sensors. And later on, our control plugins for Gazebo. So type this last piece in right now at the very end. It's a gigantic command. Okay, and when you're done doing that, press enter. All right, let's start by creating our robot base. Just going to open the folder, source, yaboom ROS master, yaboom ROS master description, URDF. Let's go to mech, and here's the base. Right click, open with text editor. Let's see. I really want get it. There we go. So right click and open with get it. So here's our blank file. Now earlier we cloned everything to our downloads folder. So let's go to description, URDF. And even though we already got this package, the whole purpose of this is to show you how we can build everything from scratch. So we're going to go into URDF. Let's go to mech. And here's the base. And I should not have clicked on it like that. Let's right click, open with, get it. Always use for this. Okay, so here is our whole file. I'm going to Control A, Control C to copy, and then Control V. Let's copy all of that into this file. So now we've got our robot base in all its glory, all in here. Okay, and let's close. Okay. This is the package. You can see Yaboom ROS master, Yaboom ROS master description. Now let's handle the wheels also in the mech folder. I'm going to open with, get it, open. Okay, and let's go to the downloads. Wheel, open with, get it. Okay, and let's copy. Control V. Okay, we're copying, pasting in that into the Yaboom ROS master description. This is our wheel definition. Okay, let's double check that. Yeah, so here's the base. That's looking good. And here's the wheel. That's looking good. Okay, that's just a generic mecanum wheel that we just added. Okay, and now let's create the RGBD camera. Okay, it's URDF, sensors, RGBD camera. All right, and an RGBD camera, RGB stands for red, green, and blue, and D stands for depth. It's like a regular digital camera that not only captures colors, RGB, but it also measures how far away everything in the scene is from the camera. That's the D. The D stands for depth. And this added depth information allows the camera to create 3D maps of its surroundings. All right, and let's add the code right now. Let's go over here to downloads, Yaboom, description, URDF, sensors. Okay, and I'm going to Control A, Control C, and let's put it over here, Control V. Okay, so Control A, Control V, we've got our whole file right there for the RGBD camera. And finally, we've got our LIDAR. Well, not finally yet. So here's our LIDAR. All right, and let's just go over here, open. All right, that's good. Let's go into the Yaboom description. Okay, we got our RGBD open. Too many files open. Let's close it all. Let's go to LIDAR, open it. Okay, here's our blank LIDAR. And let's go over to the downloads. Let's open the one from GitHub, and let's Control A, Control C to copy, and Control V to put it in our own package. That's the LIDAR. And later we will add the LIDAR plugin so we can generate simulated LIDAR. We'll actually show you how all of that works in a real gazebo environment. Okay, now let's create the IMU. So let's go back here. Let's open IMU. Okay, this is our blank file right here for the IMU. Now let's go to the downloads, and we're going to copy this whole thing, Control C, and put it into the imu.urdf.xacro. And remember to save. And let's close it all out. Okay, and let's go to URDF. Let's just take a look at the robots. Let's close all that first. Okay, let's go here. ROS2, source, Yaboom ROS master, description, URDF. This should still be blank. Yeah, good. Still blank. Okay, and now let's create the full robot, bringing everything together. So I'm in the Yaboom ROS Master description folder, URDF and robots, and you have the ROS Master X3 URDF.XACRO. Open it up. And let's go to the other one in downloads. Yaboom. And let's go to description, URDF, robots, and let's open. Control A, Control C, and Control V. And save. Everything is in there, so you can see this brings everything together. We are pulling together our robot base, our mecanum wheel, our RGBD camera, LIDAR, IMU. We don't yet need these control plugins yet. We'll use these later. So let's just delete that piece. We'll bring them back in later. And save. All right. So that's what you typically do. You would pull off the URDF from GitHub, from the manufacturer's repository, and then you'd bring those into your own package. And I did it manually rather than copying them over, but you can just as easily copy the files over into the appropriate files. I like to do it one by one just to have a look at each before I put them into my own package. All right, let's open up Visual Studio Code and let's have a look at some of these URDF files. Okay, CD, boom, code dot. Okay, we've got Visual Studio Code open, and we're going to go through the URDFs. Let's start with the base URDF right here, ROS Master X3 base URDF. So at the top, we start with an XML declaration and define that this is a robot description using XACRO, macro language for robot descriptions. Then we have a bunch of properties like the width of the robot, the wheel width, the wheel radius, the height, and the base length. Now, where did I get those values from? So I'm going to open up Firefox. Let's go to Google. And let's see, let's type Yaboom ROS Master X3. Okay, and let's see. Let's click on the first result. Let's go through here. All the way down. Scroll, 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 scroll. Somewhere in here, we've got the diagram. They make you work. They make you work. There we go. Okay, let's get, oh, no. Took me to the bottom. Let's go back, scroll back down again. Scroll back down, scroll back down. So you type Yaboom ROS Master X3. We're going to, oh, it's a beautiful diagram right there. Let's go all the way down. Love it. Okay, so here we have the ROS Master X3 dimensions, and you can just pull it right here from their documentation. You can see the numbers here, and you can match those up, true those up with what I have on the actual XACRO files here. So that was the source of these values, and that's what you'll do if you need to create these from scratch. You look at the documentation, or most likely the manufacturer, if they use ROS 2, they'll already have the URDF already ready. So you really don't need to go through all of that. So the ROS Master X3, everything here, all the tags follow the same logic as the robotic arm. So we have each link, we've got the visual tag defining how the robot looks in simulation using a 3D model. Our STL file right here, just to confirm, we'll scroll over. You can see that STL file. All right. And you've got the collision geometry. I set a simple collision geometry. In this case, it's a box, length, width, height, X, Y, Z axes. And the collision property for the link, the base link in this case, defines the boundaries of the actual base, and this is used to detect when a robot bumps into things. And we've got our inertial tag right here, which defines the robot mass and how its weight is distributed. At the bottom, we've got the gazebo tag for the base link, and that defines how the material looks in different lighting. And you should know that the math in the inertial section, all of this intimidating stuff right here, describes how the robot resists rotation around different axes. And this is important for realistic physics simulation. And the formula here, you're probably, where did we get that? Where did we get that formula, Addison? Where did this come from for the inertia? Well, that's the standard equation for the moment of inertia of a rectangular box. And it makes sense since that's the geometry we're using is a rectangular box for our collision geometry. All righty. Now let's go down to the mecanum wheel XACRO file. So I've opened up mecanum wheel.urdf.xacro, and unlike regular wheels that can only move forward and backward, remember that mecanum wheels have small rollers arranged at 45-degree angles around their circumference. This unique design allows a robot to move sideways, diagonally, or even rotate in place while remaining stationary, similar to how a crab can walk sideways. So in this file right here, we start with the basic properties of the wheel. And these measurements define the physical characteristics of our mecanum wheel. And this is also based on the documentation. We've got the wheel radius, the separation from left wheel to right wheel, the width of each wheel, the mass of each wheel, and the offsets in the X and Y direction. Now, the wheel radius affects how fast the robot moves for a given motor speed. Okay? And the separation, this wheel separation figure, influences the turning behavior. So a wider set wheel base provides more stability but requires more torque to turn the actual robot. Mass and dimensions affect the robot's physics simulation, including momentum and inertia. Next, we define a macro. Remember, a macro is like a template that we use to create our wheel. And the macro is pretty clever. Instead of writing separate code for each wheel, we just write it once and use parameters to customize it. So the prefix parameter right here helps us name each wheel. So like front left wheel or right wheel or rear right wheel. And the X reflect right here and the Y reflect parameters are either 1 or -1, letting us mirror the wheel's position and orientation for different corners of the robot. The visual component defines what we see in the simulator. You can see that right here. And you can see that we load a 3D STL file of the actual wheel. Okay, that's this right here. RPY, that's roll, pitch, and yaw, right there. Those parameters ensure the wheel is oriented correctly. We have a dark gray color right here, which makes it easy to distinguish the wheel from other robot parts. For physics simulation, we need a collision model for the mecanum wheel. While the visual model can be complex and detailed, the collision model needs to be kept simple for computational efficiency. So we don't use the detailed STL model for collision detection. I don't recommend it. It just makes things move much quicker when you use basic geometry. It speeds up the physics calculations, and it also helps to maintain accuracy as well. So you get the kind of the good trade-off right there. Now we have our inertial properties right here that defines how the robot behaves physically. And these seemingly very complex formulas are based on physics equations for a cylinder's moment of inertia. It determines how the wheel resists changes in rotation around different axes. The joint configuration defines how the wheel connects to the robot. Right here, the base link of the robot. And a continuous joint right here means the wheel can rotate indefinitely in either direction. This axis specification right here means that the wheel rotates around the y-axis of the parent link. And in this case, the parent link is the base link. And then finally at the bottom down here, last but not least, we have our gazebo specific settings right here. This up top sets the friction coefficients. Okay, and we set some low values for smooth rolling over the surface. And you can see our mu and mu2 values are very, very low. And we keep it low because we want to allow sideways movement for the mecanum wheeled robot. Higher values would make the wheels grip too much on the surface and resist the beautiful sliding motion that you get that makes mecanum wheels so special. And that's it. Also the color down here. Now to implement this on your own robot, you need to call this macro 4 times, 1 for each wheel. Now let's open the RGBD camera. So we go to Sensors, RGBD camera. An RGBD, red, green, blue, and depth camera combines a regular color camera with depth sensing capabilities. This allows robots to not just see colors and shapes, but also understand how far away objects are, which is important for navigation and manipulation tasks. So in our code, we start by defining a macro called RGBD camera with a number of parameters that make the camera highly configurable. Don't be intimidated by all of these numbers. These parameters control everything from the basic naming of the camera and positioning to detailed physics properties. The default values are carefully chosen to match real-world RGBD cameras. I got all our values here. You can see the mass right here set to 0.072 kilograms. And we've got precise inertial properties that match the Intel RealSense's the D435 camera we're using, the physical characteristics. Let's scroll down. Down here, we've got the camera's physical structure, which consists of multiple frames or coordinate systems, each serving a specific purpose. Okay, and we've got the main camera link right here, main camera link, that holds the visual 3D model and can optionally include collision geometry for physical simulation. All right, and this aluminum material right here, for the material, we're using aluminum. Right here, you can see material name aluminum. That gives the camera a realistic appearance in Gazebo simulation engine. So what makes this file particularly interesting and particularly sophisticated is its handling of all of these multiple camera frames. So if you go through here with a fine-tuned comb, you can see infra, you can see a lot of different frames. We've got the depth frame. The depth frame captures distance information. We've got the infrared frames, Infra 1 and Infra 2, which are used for stereo depth perception. We've got the color frame down here, which is like the regular RGB camera. And we've got our optical frames, which are aligned to standard ROS conventions. And each frame is connected by joints. Joints. And you guys know joints. You remember that from the robotic arm discussion. That links all the pieces of the camera together. And now we've got our Gazebo simulation settings. It defines how the camera operates in simulation. That's it for the RGBD camera. Now let's look at the IMU URDF. Very similar to the RealSense URDF, The difference is that this IMU file, IMU URDF.XACRO, defines an IMU sensor. And this, what is an IMU? So an IMU stands for Inertial Measurement Unit, and it measures a robot's orientation, acceleration, and angular velocity. It tells the robot which way is up, how fast the robot's moving, and how the robot is rotating in space. Just like the sensor in your smartphone that knows when you turn your screen horizontally and vertically. That's an IMU at work. And the core macro definition starts with a lot of configurable parameters that let you customize how the IMU is attached to your robot. The physical properties of the IMU are carefully defined to match real-world characteristics. We can see the sensor is 0.031 kilograms or 31 grams right here. See that the measurements, it's roughly 39 millimeters by 38 millimeters by 13 millimeters. We can see that the IMU updates measurements 15 times per second or 15 hertz. And it is rendered in a dark black color to match typical IMU hardware, like the fidgets, for example. I love the fidgets IMU. It's very, very nice. One of the more common IMUs that you will find in robotics projects. And one of the more interesting parts is how the code calculates the moment of inertia. Again, it's a measurement of how hard it is to rotate this particular sensor, the IMU, around different axes. These calculations comes from physics equations, folks, for rectangular objects. The 1/12 right here, this mass over 12 factor, appears because of how mass is distributed in a rectangular shape. Each axis needs different calculations because rotating a rectangular object requires different amounts of force depending on which way you're turning. The visual representation keeps things simple, just a simple black box shape. Similar to the fidgets IMU. And now we've got our joint, and this shows how the IMU attaches to the parent frame, which is the base of the robot. And the fact that this is a fixed joint means the IMU does not move when the robot moves, which is what we want. And then at the bottom, we've got our simulation settings for Gazebo, and that defines how the IMU behaves in the virtual world. So what does this mean? Okay, what does all of this gobbledygook mean in the Gazebo reference? Well, you're creating a virtual IMU sensor that publishes its data to a ROS topic called IMU data. IMU data, topic name. And where do we get the topic name? That funnels in from here. Okay, and you can change it to whatever you want, but I like to keep it IMU data. And the visualization of the IMU data is turned off by default, since typically you don't need to see sensor data graphics like the IMU during simulation. Now let's take a look at the LIDAR file. Open up LIDAR.URDF.XACRO. And this file defines the LIDAR, which means light detection and ranging sensor, for a robot simulation in our program. It specifically models the RP LIDAR S2. So how does a LIDAR work? Well, a LIDAR sensor spins around and around, and it uses laser beams to measure distances to objects. It creates a 2D map of its surroundings. So in this file, we start the macro off by, again, defining the physical and operational characteristics of the sensor. And the physical properties match the real RP LIDAR S2. The real one. And you get that from the data sheet. You will search for the data sheet of this particular LIDAR. Just Google RP LIDAR S2 datasheet and you'll find it. You can see right here, our LIDAR has a mass of 185 grams. Right here, this is in kilograms, so 0.185 kilograms. It's got a width of 77 millimeters and a height of 39.8 millimeters. And like most LIDAR sensors, we're rendering it in black to match real hardware. We treat the LIDAR's moment of inertia as a cylinder, since most LIDARs are shaped like a cylinder. All right, and everything else is fairly the same in here from our other files, just different parameters, but everything is pretty much the same sort of logic, where we define the link, the collision geometry, inertia, and all that good stuff. And here you can see the gazebo piece down here. Okay. And that helps us determine exactly how the LIDAR is going to publish its data. So things like the update rate, if it's always on, if you want to visualize the LIDAR data, what's the topic name, what's the minimum angle that the robot LIDAR can see, what's the maximum angle, and all of these come from these properties here. You can see the minimum angle is minus pi and maximum is pi. So the data from this LIDAR I've chosen to match very closely to a real-life RP LIDAR S2 for navigation, complete with that 360-degree field of view. And I've updated the update rate, this is the publishing rate, to 10 hertz, because typically I really like using the RP LIDAR S2, and on most of my robots, I'm getting about 10 hertz. So all of these values very, very closely match a real RP LIDAR S2. Okay, now let's go over to the robots folder, and we're going to click ROS Master X3, URDF.XACRO. This is the main assembly file for the ROS Master X3 robot. Think of it as a blueprint that brings together all the individual components we looked at earlier in this tutorial. This puts it all together to build a complete robot. And you can see here at the top, we're importing using the include right there, XACRO include. We're including all of the various files. First one is the base, which we covered, mecanum wheel, file, the RGBD, LIDAR, and IMU. All of our imports. We've got different constants that we want to define up here, and variables so this is the constants, this is the variables right here. This is pi, and here's the robot name, prefix, and for example, you might use a prefix if you just want to create a specific name that's prepended to the robot name, and then whether you want to use gazebo or not when you launch this XACRO file. We've got our 4 wheels right here, 1, 2, 3, and 4. Our RGBD camera, we're using the macros from that, the macros for the LIDAR, and the macros for the IMU. That's assembling our robot in this centralized file. And we add different parameters here to determine the orientation and offset. Remember those parameters for each of the sensors? Here is where we actually set the values. Okay, and you can see here, for example, RP LIDAR S2, it is mounted 8.25 centimeters above the base of the robot. And it's perfectly level. You can see 0, 0, 0, roll, pitch, yaw. It's perfectly level to scan the horizontal plane around the robot. And then finally, we add the IMU sensor down here. Now, the IMU sits very close to the base, like 0.6, right here, 0.006 meters, right there, or 0.6 centimeters up, because it needs to measure the robot's core movement. So this whole assembly robot creates a mobile robot. The Yaboom ROS Master X3 models the entire robot, and this robot can move in any direction because it has its beautiful mecanum wheels. It can see objects in depth with its RGBD camera. It can see obstacles using its LIDAR. And it can also track its movement and orientation using its IMU sensor. All of these sensors work together in unison. The LIDAR maps the space, the camera identifies objects, and the IMU helps keep track of the robot's position and movement in the world. The mecanum wheels let the robot navigate precisely through its environment. Now that we've covered the details of the URDF, it's time for some action. And again, I'm going to show you the build alias we created earlier, where all the build alias does is it changes directories into your ROS2 workspace. It then runs colcon build, and then you source the bash. And that's what I'm going to run here. Let's clear and then run build. There he is, nice and finished. Okay, now it's time for the fun part. I'm going to close this, close that. Let's clear the terminal. Okay, let's just source the bash, clear. And for those of you following at home, I just want to show you, so here in this source bash RC, I'm actually sourcing ROS2. Okay, you need to make sure you do that and then source the ROS version. So I have all of this that automatically runs every time I open a new terminal window. So a lot of times in ROS2, you'll see people run this command manually, sourcing ROS2, but I don't need to do that because everything's all in my bash RC, and that's the way you should have it too. We try to make our lives easier over here at Automatic Addison. Now let's visualize the URDF. So I'm going to do ROS2 launch URDF tutorial. Okay, display.launch to model equals, and I'm going to copy the path. Okay, from another spot, and let's paste it. Okay, so let's just go through that command slow and smooth. So we do ROS2 launch URDF tutorial package. We're launching the display.launch.py launch file, and we are feeding it the model, the full model of the full robot, that assembly, full assembly, that last URDF that we examined. All right, and when you're ready, press enter. Oh, wow. Look at that beauty. Look at that beauty. Ho, 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 ho. Ha, ha, ha. Now, by convention, the red axis is the x-axis, the green axis is the y-axis, and the blue axis is the z-axis. And that's for all of the different coordinate frames of your robot. So that we can actually see our robot in all its glory, let's expand this out. Let's zoom in using the middle mouse, uncheck TF, and there it is. Beauty. There's our IMU right there, this black box right there. Very much resembles. Let me show you the fidgets IMU I was talking about earlier. Fidgets, IMU, mote, mote 0110. So fidget IMU mote 0110. Let's click on it. And you can see the IMU right here. Just like we are modeling it in the virtual world. So that's the fidgets IMU. We have our RP LIDAR S2 up top. I'm going to go to here and let's go to Google. RP LIDAR S2. You can see the RP LIDAR S2 right there. Looks very similar to the way we've modeled it. Let's go back to RViz and our Intel RealSense camera on the front looking upwards. So let's take a look at that. RP LIDAR, Intel RealSense D435 depth camera. Let's go to image. There it is right there. This is our depth camera. This is the one that I'm modeling. You can see what it looks like when it's all broken apart over here. And it's different components. Actually pretty cool that all of this stuff is in this tiny little compartment. Very neat. And here are our mecanum wheels. Let's zoom in. You can see they're angled at 45 degrees to help us get multi-direction navigation and movement, sideways, forward, back, turns. All right. And let's use this GUI. So to move the wheel. So here, you can see right here, we're turning the wheel. And this one, turning the wheel. So just play around. Let's open up this. All right, and the displays panel, you can just play around with the different things over here. So let's take a look. Under robot model, let's undo visual enabled, and let's take a look at collision enabled. You can see what the collision geometry looks like. I set it to be a box on wheels. Okay, and let's look at mass. You can see the mass here, how the mass looks. Inertia, modeled. Bring back visual enabled so you can see the robot. So that collision enabled, those red pieces that we just looked at. Let's see here. Let's go on, check that. Collision enabled right here. You can see what the simulation engines use to detect collisions on the mobile robot. So when the mobile robot is commanded to go to a certain point, it'll check that collision geometry to decide, oh, you know, it can get through there and get through there and so forth. So that's good. And finally, let's go check out the coordinate frames. So let's go CD documents. And let's do ROS2 run TF2 tools and then view frames. Now, what are we doing here? We want to see the coordinate frames of the mobile robot. So it's listening to all the transforms, and we should have a PDF that showed up. And I see we do. I see we do. We can see our PDF. So let's do events. We need the one for today because today is April 28th. So frames 28.pdf. So events is the program that you use to view. Enter. And here, when we zoom in, you can see our coordinate frame. So we have the base footprint, the base link, and everything connects over here to the base link. We've got the wheels that connect to the base link. Got the camera that connects to the base link, the IMU, the laser frame, the LIDAR frame. And then the camera's got different frames, which you remember from going through the URDF itself, which are fixed to the main camera link. Everything goes back up to the base link. It's the parent of everything, and then that connects to the base footprint, which is a projection of the base of the robot on the surface. So now we'll Control C. I'm going to remove these files. We don't need them anymore. I like keeping my directories clean. And so now when we want to visualize our robot in the future, let's add an alias. And the alias that you're going to add is this command right here. Okay, and take some time. Maybe you want to pause the video and take a look at it. So echo alias yaboom ROS to launch URDF tutorial display.launch.py, and then the path to the model. And then we're going to output that to the bash RC file. So once you get that, press enter. And to see it was added, do a cat bash RC. And you can see it down here. The yaboom right here was added. Let's do a source, the bash RC. Okay. And now I want you to type yaboom. Yaboom. And there we go. Take the TF out, and we can see our robot in all its glory now. Pretty cool. Ooh, the wheel. Let's get a little closer. Moving it forward and backwards. And that's it. That is our short code, our alias for showing the robot very quickly. So you don't need to type in that long monster command every time. So that is it for this tutorial. Keep building, and I will see you in the next tutorial.